Yeah, well, thank you everybody who had a hand in inviting me here. I've been enjoying your hospitality, and I'm sorry I'm here only such a short time not to get to know more of you. Anyway, I should apologize for reading from a text which I normally, if I were talking about a subject that I actually understand, I would talk extemporaneously. But since I'm talking about a subject in which I know about as little as you, I prefer to stick to the text. So anyway, here it goes. So in February 1943, Dublin was an oasis of peace in a Europe at war, one of the few places where deep thinkers and scholars could find refuge. Thanks to the hospitality of Ireland and of Eamon de Valera, the physicist Schrodinger was here. He gave at Trinity College a series of 7 lectures with the title, "What is Life?" to an audience of 400 people. He tells us with pride that the audience did not substantially dwindle. He applied for the first time the way of thinking of a quantum physicist to the basic problems of biology. And he had a good command of the English language. Fortunately, his lectures were published in 1944 by the Cambridge University Press, and I was lucky to buy a copy of the first edition in February 1945 while the war was still raging. His message came like a winter sunrise, bringing light to the dawn of the new age of biology. Here is the opening statement from Schrödinger's book. So now I quote from Schrödinger: "We have inherited from our forefathers the keen longing for unified, all-embracing knowledge. The very name given to the highest institutions of learning reminds us that from antiquity and throughout many centuries, the universal aspect has been the only one to be given full credit. But the spread, both in width and depth, of the multifarious branches of knowledge during the last 100 years has confronted us with a queer dilemma. We feel clearly that we are now only beginning to acquire reliable material for welding together the sum total of all that is known. But on the other hand, it has become next to impossible for a single mind fully to command more than a small specialized portion of it. I can see no other escape from this dilemma than that some of us should venture to embark on a synthesis of facts and theories, albeit with second-hand and incomplete knowledge of some of them, and at the risk of making fools of ourselves. So much for my apology." So that's a quote from Schrödinger. So I take courage from Schrödinger's example. Like him, I am a physicist venturing into biology. Like him, I take the risk of making a fool of myself. Like him, I'm asking a question. His question, "What is life?" was timely and enormously fruitful, although he did not answer it. I hope that mine will be equally timely and equally fruitful. Compared with his bold speculations, mine are modest. He gave 7 lectures and explored his subject deeply. I gave only 1 and barely scratched the surface of mine. With thanks for the hospitality of Ireland and the Dublin Institute for Advanced Studies, I'll now begin. I should then just give you a table of contents that just to get an idea of what the talk's going to be about. So 1, homage to Schrödinger. 2, the road not taken. 3, dynamic quantum clustering. 4, the failure of artificial intelligence. 5, maps and feelings. 6, the Endicott House meeting. 7, mathematics as a tool for understanding nature. And 8, quantum analog computing. So this is now section 2, which is the road not taken. The title of the talk is "Are Brains Analog or Digital?" We know that creatures like us have 2 quite separate systems for processing information, the genome and the brain. We know that the genome is digital, and we can accurately transcribe our genomes onto digital machines. We cannot transcribe our brains, and the processing of information in our brains is still a great mystery. I will be talking about real brains and real people, asking a question that will have practical consequences when we are able to answer it. Of course, I'm not able to answer it now. All I can do is examine the evidence and explain why I consider it probable that the answer will be that brains are mainly analog. Robert Frost said it. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. So in the 1930s, there were 5 kinds of computers available for doing serious calculations. 2 of them were digital, the Marchand calculator for doing accurate arithmetic, and the Hollerith card punch machine for tabulating big masses of data. 3 of them were analog, the slide rule for doing fast arithmetic with 3-figure accuracy, the Bush differential analyzer for solving differential equations, and the Lehmer photoelectric number sieve for solving equations in integers and factorizing big numbers. The Lehmer machine worked with integers, but was still an analog machine. It did calculations using finite Galois fields and identified integers by counting holes in a wheel, not by a digital code. But then in 1936, Alan Turing wrote his paper on computable numbers, which revealed the power and beauty of digital computing as an abstract logical construction. After that, analog computers slowly went out of fashion. Analog computers became the road not taken. I still used to use my slide rule for calculating my income tax until the 1980s, when the tax collectors of the state of New Jersey demanded 4-figure accuracy in the calculation of interest rates. For 4-figure accuracy, I was forced to switch to a digital calculator. Now we're so immersed in a world of digital computers that it's hard to imagine things going the other way. If it is true that brains are analog, then we must sooner or later take the road that Turing did not take and explore what analog computers can do. There are good reasons why the world of science and commerce went digital in the 20th century. Digital data and digital calculation have huge advantages over analog in accuracy, in speed, and in reliability. There are many situations in life and in business where 3-figure accuracy is not good enough. There are even some situations in science where 12-figure accuracy is not good enough. For all kinds of practical purposes, digital computers are here to stay. But the brain has big advantages in flexibility and versatility. The brain somehow manages to do a dozen different jobs, seeing and hearing and walking and talking and thinking and controlling our vital functions, all at the same time, without getting confused. If it is true that the brain is an analog machine, then we should be able to build analog machines with the same kind of flexibility and versatility. That possibility is the subject of my talk. So, section 3, dynamic quantum clustering. One of the big unsolved problems of the modern world is to convert information into understanding. This is a big problem in science, in government, in business administration, and in economics. In each of these areas, we have huge amounts of information and very limited understanding. As a result of the rapid progress of digital technology, it has become far cheaper to collect information than to understand it. Recently, a new method called dynamic quantum clustering has been invented to extract small nuggets of understanding from large amounts of information. I'm grateful to my friend Marvin Weinstein, who is one of the inventors of dynamic quantum clustering, for telling me about it. The idea of dynamic quantum clustering is to present the information in a large database to a human viewer in the form of a moving picture, using a mathematical algorithm borrowed from the motion of systems of particles in quantum mechanics. The quantum mechanical motion is entirely fictitious. It does not represent any process happening in the real world. It is designed simply to make a big collection of data understandable to a human brain. The human brain is at home in the world of moving pictures. It can pick out structures in moving pictures quickly and efficiently. After the human viewer has called attention to a structure, the dynamic quantum clustering program can record the structure and analyze it using digital processes. The human eye and brain serve as a subroutine in a digital program, making use of the brain's peculiar skill in extracting structure from patterns of movement in space and time. In Weinstein's paper, which I give the reference to, that's published 2013, the dynamic quantum clustering method is illustrated by applying it to big databases in 5 different fields: nanochemistry, condensed matter physics, biology, seismology, and finance. In each field, the method finds subsets of the data that contain important information. The information remains hidden if the data is analyzed by digital processes. For example, in the field of nanochemistry, the object of study is a fragment of an ancient Roman pot, and the hidden structure is a filamentary distribution of oxidized and reduced phases of iron. Similar structures are found in the electrodes of lithium-ion batteries, in human bones, and in Roman pots. The filaments are evidence that the same kind of chemical reactions are occurring in all 3 materials. The chemistry of the lithium-ion electrodes was understood first, and the understanding could then be transferred to the bones and the pots, materials that are less accessible to laboratory measurements. Weinstein describes the purpose of dynamic quantum clustering. Look for the needle in the haystack, determine what it is, and find what this means. The reason why dynamic clustering is powerful is that you discover the needle without knowing in advance what you're trying to look for. You do not need to write a detailed description of the needle into the search algorithm. The human brain has the capacity to make unexpected discoveries. So I see dynamic quantum clustering as the first step on a long road to create islands of understanding in a sea of information. To progress further along this road, we must not only exploit the marvelous faculties of the human brain, but also understand how they work. Practical use of dynamic quantum clustering for exploring databases must go hand in hand with neurological exploring of the brain. The first big mystery to be attacked is the physical basis of memory. We know that the brain has at least 2 systems for recording memory, one short-term and one long-term. We have no idea how memories are encoded, either chemically or physically. After that mystery is resolved, we may go further to attack the second great mystery, how memories are accessed and retrieved. The logical structure of our memory system appears to be associative. We retrieve a memory by following a chain of thought that connects it with another memory, but we have no understanding of the language the brain is using to encode a chain of thought. If we can ever develop a version of dynamic clustering that incorporates a chain of thought, it will become a far more powerful tool for converting information into understanding. I'm not here to talk about particle physics, but I have to make a brief digression to discuss the application of dynamic quantum clustering to the understanding of particle experiments. Recently, the world has been celebrating the discovery of the Higgs particle at the Large Hadron Collider in Geneva, a huge and expensive particle accelerator at the European Centre for Nuclear Research. The Higgs particle is indeed an important discovery, and Peter Higgs and François Englert richly deserved the Nobel Prizes which they won for predicting the existence of that particle 40 years before. I'm happy that the particle is finally discovered after many years of effort. But I'm unhappy with the way the particle was discovered. The Large Hadron Collider is not a good machine for making discoveries. The collider makes protons collide at very high energies, and every collision makes a big cascade of uninteresting particles, background that swamp the detectors. Only a tiny fraction of rare collisions produce Higgs particles. The background of uninteresting events is so enormous that the machine cannot possibly look at them. The only way to see the rare Higgs particles is to write into the program that controls the detector detailed instructions for saving those rare events and discarding the others. The Higgs particle was only discovered with this machine because we told the machine what we expected it to discover. It is an unfortunate deficiency of the Hadron Collider that it cannot make unexpected discoveries. Big steps ahead in science usually come from unexpected discoveries. It remains to be seen whether an analysis of the Hadron Collider data with dynamic clustering methods might enable the Hadron Collider to make unexpected discoveries. Unfortunately, the data stream from the collider is so intense that it is impossible to display it without some drastic pruning. If something unexpected is hidden in the data, even if dynamic clustering is used to look at it, there is a risk that the unexpected treasure gets chopped out in the pruning. I think the future of particle experiments belongs to passive underground detectors. These are detectors looking for rare high-energy particles coming from outer space. Nature provides a generous supply of astronomical accelerators distributed over the universe, accelerating particles to far higher energies than we can reach with our biggest devices. Together with the rare high-energy particles come numerous low-energy particles that do not penetrate so far underground. Detectors are put deep underground so as to eliminate almost all the uninteresting background events. Deeply penetrating particles are rare enough so that every event in the detectors can be recorded and examined in detail. If some new species of particle or some new kind of interaction is present in the detectors, it will be seen. The detectors do not need to be told in advance what they're supposed to discover. Big passive detectors are expensive, but they're still much cheaper than the Hadron Collider. If high-energy particle experiments are to make unexpected discoveries, this is probably the best way to go. Section 4, the failure of artificial intelligence. So now I come back from the digression to particle physics, to brains and computers. I'm looking for evidence to confirm or to refute the hypothesis that the brain is more analog than digital in its operation. So my first piece of evidence is the failure of artificial intelligence. 60 years ago, when the digital revolution was beginning and the pioneers of digital computer technology were dreaming of future triumphs, one of their grand dreams was the creation of artificial intelligence. Artificial intelligence was imagined as a digital computer that could think and act and communicate like a human brain. Artificial intelligence meant a digital machine that would be as smart as a human. Many brilliant and ambitious people devoted their lives to this dream. 20 years later, my friend Sir James Lighthill was asked by the British government to advise the Science Research Council about the support of research in artificial intelligence. Lighthill wrote a famous report with the title Artificial Intelligence, a General Survey, which made him a lot of enemies. Lighthill divided the artificial intelligence activities into three categories, A, B, and C. Category A was advanced automation, the development of automatic control machinery for practical purposes. Category C was central nervous system research, the use of computers for scientific study of neurology and psychology. Category B was supposed to be the bridge between A and C. Category B was the building of robots, not for utilitarian jobs, but for imitating the behavior of human beings. Lighthill discussed the progress that had been made by the year 1972, that was when he was writing, in those three areas, and then delivered his verdict. He concluded that areas A and C were legitimate programs of research, A belonging to engineering and C to science. The work in A and C was moving ahead more slowly than had been expected. Two of the most important projects in Area A were automatic speech recognition and automatic translation, both of which had failed miserably. Three important objectives in Area C were the understanding of memory and the understanding of learning and forgetting, none of which had been achieved. But work in the areas A and C still had great promise for the future and deserved continued support. On the other hand, Area B had no scientific substance. The bridge between A and C did not exist. A and C should be supported as separate enterprises with separate tools and separate objectives. Area B did not deserve support. So here is Lighthill's sketch of Area B, which I quote now from Lighthill. Most robots are designed to operate in a world like the conventional child's world as seen by a man. They play games, they do puzzles, they build towers out of bricks, they recognize pictures in books, bear on rug with ball. Although the rich emotional character of the child's world is totally absent. A relationship which may be called pseudo-maternal comes into play between a robot and its builder. Now another 40 years have gone by, and Lighthill's verdict on artificial intelligence still stands. A lot has happened in those 40 years in Area A. In Area A, after 40 years of blood, sweat, and tears, the dragon programs of automatic speech recognition are finally working well, and automatic translation programs are producing results that are imperfect but useful. In Area C, there's been less progress, and in Area B, none at all. Progress in understanding the human brain has come from new physical tools, functional magnetic resonance image, and genome sequencing, rather than from new ideas about neural circuitry. Progress in building autonomous robots has come from imitating insects rather than from imitating humans. Artificial intelligence, after 60 years of strenuous efforts in many countries, is still, on balance, a failure. So I'm saying the failure of artificial intelligence was no accident. It failed because the goal was to imitate an analog device, the human brain, with a digital device, the electronic computer. The successes in Area A with speech recognition and translation were possible because speech and written language are handled by special areas of our brains which have evolved to process digital information. If I'm right, the successes of artificial intelligence using digital machines will be limited to those areas. So next, Section 5, Maps and Feelings. Another striking fact that we know about brains is that they use maps to process information. Information from the retina goes to several areas of the brain where the picture seen by the eye is converted into maps of various kinds. Information from sensory nerves in the skin also goes to areas where the information is converted into distorted maps of the body. The brain is full of maps, and a big part of its activity is transferring information from one map to another. As we know from our own use of maps, mapping from one picture to another can be done either by digital or by analog processes. Because digital cameras are now cheap and film cameras are old-fashioned and rapidly becoming obsolete, many people assume that the process of mapping images in the brain must also be digital. But the brain has evolved over millions of years, and it does not follow our ephemeral fashions. A map is in its essence an analog device, using a picture to represent another picture. And the imaging in the brain may be done by direct comparison of pictures rather than by translation of pictures into digital data. Introspection tells us that our brains are spectacularly quick in performing two tasks essential to our survival in a natural environment: the recognition of images in space and the recognition of patterns of sound in time. We recognize a human face or a snake in the grass in a fraction of a second. We recognize the sound of a voice or a footstep equally fast. The process of recognition requires the comparison of a perceived image with an enormous database of remembered images. How this is done in a quarter of a second with no conscious effort, we have no idea. It seems likely the scanning of images in associative memory is done by direct comparison of analog data rather than by digitization. Another fact that we know for sure is that our processing of sensory information is strongly coupled with emotions. Seeing and hearing and smelling are inextricably mixed up with feeling. A big part of human enterprise and creativity is devoted to the arts. Music to explore the emotional dimensions of hearing, painting and architecture to explore the emotional dimensions of seeing. Our perception of sensory information is concerned with quality much more than with quantity. Subjective impressions may be misleading, but our emotional response to music or to a beautiful landscape suggests we are processing sounds and images as shapes rather than as digits. The glory of a desert sunrise or of a Rembrandt painting belongs to the whole scene and not to the individual pixels. As a general rule, our perception of sensory information appears to be continuous rather than discrete. But there is one important exception to this rule. The exception is our perception of language. Spoken language is digital, using a finite set of discrete phonemes to convey meaning. Our auditory system is trained to convert a continuous flow of sound into a discrete sequence of phonemes, and then to convert a sequence of phonemes into words and sentences. There are specialized areas of the brain, mainly in the left hemisphere, where this digital processing of information is done. Written language is also digital, and there are other areas of the brain where visual images are translated into digital sequences of letters or ideograms. The invention of Braille allows blind people to transfer the process of digital translation from visual to tactile information. These capabilities give us proof that certain parts of the brain are digital, processing phonemes or written symbols as discrete objects. But our understanding of language is also associated with strong feelings and emotions that go far beyond the processing of sounds and symbols. language is not perceived by us as a string of phonemes. A big part of our culture is concerned with art forms arising from language, poetry and drama and preaching and storytelling. Beyond the digital words and phrases, there is a whole world of literature. We perceive literature as having style and sparkle, depth and resonance. Our perception of literature belongs to the overall shape of the language, not to the individual words. The quality of a poem such as Homer's Odyssey or Eliot's Wasteland is like the quality of a human personality. A large part of our brain is concerned with social interactions, getting to know other people, learning how to live in social groups. The observed correlation between the size of brain and the size of social groups in primate species makes it likely that large brains evolved primarily to deal with social problems. Our ability to see others as analogues to ourselves is basic to our existence as social animals. The computer engineer Danny Hillis published 25 years ago a delightful speculation with the title Intelligence as an Emergent Behavior, or The Songs of Eden. This was published in 1988. He tells a story to describe how it might have happened in the evolution of humans that music came first and speech came second. So now I quote from Hillis. Once upon a time, about 2.5 million years ago, there lived a race of apes that walked upright. The young apes, like many young apes today, had a tendency to mimic the actions of others. In particular, they had a tendency to imitate sounds. Some sequences of sounds were more likely to be repeated than others. I will call those sequences songs. The songs survived. They bred, competed with one another, and evolved according to their own criterion of fitness. One successful strategy for the competition between songs was for a song to specialize, to find a particular niche where it would be likely to be repeated. Once the songs began to specialize, it became advantageous for an ape to pay attention to the songs of others and to differentiate between them. By listening to songs, a clever ape could gain useful information. Once the apes began to take advantage of the songs, a mutually beneficial symbiosis developed. Songs enhanced their fitness by conveying useful information. Apes enhanced their fitness by improving their capacity to remember, to replicate, and understand songs. So evolution created a partnership between the songs and the apes, which thrived on the basis of mutual self-interest. Eventually, this partnership evolved into one of the world's most successful symbionts, us. So this fable of Danny Hillis may not be true, but it explains two great mysteries of human evolution, which are otherwise hard to understand. Why did we evolve people like Mozart and Beethoven? And why did we evolve people like Sophocles and Shakespeare? It seems that we have far greater capacity for composing and appreciating music, and far greater capacity for elaborating and enjoying speech than would be required for surviving in a primitive environment. Hillis explains the existence of Mozart and Beethoven by evolving music first, with the songs competing for survival on the basis of musical quality. He explains the existence of Sophocles and Shakespeare by evolving speech second, with the songs competing for survival on the basis of meaning. A song with meaning attached evolves into speech. with the quality of the song evolving into quality of the speech. This version of our history explains the amazing fact that a bunch of apes only recently descended from the trees can produce great composers and poets. The evolution of great works of art depends on the quality of the music and the poetry, not on the digital language of the notes and the syllables. So I'm suggesting the brain is mainly an analog device with certain small regions specialized for digital processing. It is certainly not true, as sometimes claimed by pundits talking on television, that the left hemisphere is digital and the right hemisphere is analog. It seems to be true that most of the digital processing is done on the left side, but the division of labor between the two hemispheres is still largely unknown. So section 6, the Endicott House meeting. 33 years ago, in May 1981, we had a meeting at Endicott House, a clubhouse owned by MIT in the American Cambridge, talking about the future of computing. The meeting was organized by Tom Toffoli, and a lot of bright people were there, including Danny Hillis, Richard Feynman, Charles Bennett, and two people I had not heard of before, Marianne Pourel and Ian Richards. Charles Bennett talked about his recent discovery that digital computing could be done reversibly without erasing information and without dissipating energy. Hillis talked about parallel computing, and Feynman talked about quantum computing, two subjects which later turned out to be important. But to me, the most exciting news at the meeting came from Pourel and Richards, two mathematicians who were then at the University of Minnesota. Marianne Pourel and Ian Richards proved a theorem that says in a mathematically precise way that analog computers are more powerful than digital computers. That was published in 1981. They give examples of numbers that are proved to be non-computable with digital computers, but are computable with a simple kind of analog computer. Alan Turing had defined computable numbers to be those that can be computed with digital machines. The numbers discussed by Pourel and Richards are analog computable, but not Turing computable. An analog computer deals directly with continuous variables, while a digital computer deals with discrete variables. The Pourel and Richards computer is a classical field propagating through space and time and obeying a linear wave equation. The classical electromagnetic field obeying the Maxwell equations could do the job. Pourel and Richards show that the field can be focused on a point in such a way that the strength of the field at that point is not computable by any digital computer, but it can be measured by a simple analog device. The imaginary situations that they consider have nothing to do with biological information. The Pourel-Richards theorem does not prove that analog brains are better than digital brains. It only makes that conjecture more plausible. Charles Bennett recently sent me a picture of the people at the Endicott House meeting. Pourel and Richards are there in the picture, two young people who had done something extraordinary. I don't know what happened to them afterwards. I had the feeling I was the only person at the meeting who took their work seriously. They had done for analog computing the same job that Alan Turing had done for digital computing 45 years earlier. Turing published his classic paper, Computable Numbers, in 1936. Pourel and Richards published theirs in 1981. Both papers took a long time to attract attention. My son George recently published a book with the title Turing's Cathedral, describing the magnificent edifice of knowledge and power that grew out of Turing's paper. Poor Ellen Richards' cathedral has not yet begun to grow. Science fiction writers gave us a picture of digital life and a picture of analog life long before we could decide which picture comes close to describing humans. To visualize digital life, think of a human consciousness downloaded from a brain into a digital computer, like the character Hal in the Stan Kubrick movie 2001. To visualize analog life, think of a human consciousness uploaded into a black cloud, as described in the science fiction novel by Fred Hoyle. The black cloud is an analog device with its memories encoded in magnetic fields generated by dust grains moving through the cloud. If we are analog life, our downloading into a digital computer may involve a certain loss of our finer feelings and qualities. That would not be surprising. I certainly have no desire to try the experiment myself. Perhaps when the time comes for us to adapt ourselves to a cold universe and to abandon our extravagant flesh and blood habits, we should upload ourselves into black clouds rather than download ourselves into silicon chips. If I had to choose, I would go for the black cloud every time. So now I'm going to skip to section 9, the mathematics as a tool for understanding nature, and so that'll be in the written version. And so now comes the last section, quantum analog computing. During the last 30 years, a big new enterprise has grown up with the brand name quantum computing. This enterprise aims to imitate the architecture of ordinary digital computers using quantum spins instead of classical on-off switches as carriers of information. A quantum spin means an atom or a collection of atoms with a spin obeying the rules of quantum mechanics. The machines built in this way are quantum digital computers. The holy grail of quantum digital computing is to implement the Shor algorithm. 18 years ago, Peter Shor astonished the world by inventing an algorithm which a quantum computer can in principle use to factorize large integers in polynomial time. Polynomial time means the number of computer operations required is less than some power of the number of digits in the integer to be factored. The finding of factors of a large integer is a notoriously hard problem for classical computers not using quantum processes. It is generally believed, but not proved, that a classical computer cannot factorize large integers in polynomial time. The security of various public key encryption systems depends on the impossibility of rapid factorization. The Shor algorithm constitutes a threat to the security of such systems. But the threat to secure encryption becomes real only if the theoretically superior power of quantum digital computers can be embodied in real hardware. Quantum computing today is at roughly the same stage of practicality as classical computing in the days of Charles Babbage in the early 19th century. Babbage had the right concepts, but he lacked the physical tools to make his concepts useful. He tried to build an analytical engine out of mechanical clockwork, a project that absorbed his time and money and strength for many years and inevitably failed. When I was a boy in London, I used to gaze in fascination at the relics of Babbage's analytical engine preserved in a glass case at the Science Museum in London. If we should try to build a quantum computer today, its fate would probably be similar. The quantum devices that we have available today are not much better than Babbage's clockwork. But I'm asking whether our brains, or parts of our brains, might be quantum analog computers. I believe this possibility was first suggested by Richard Feynman. The idea is that the brain might be an amplifier, sensitive to the quantum states of some special molecules constituting a molecular memory and amplifying the molecular information until it becomes a signal strong enough to drive motor neurons to action. In this way, the brain would be able to use quantum jumps in the memory, which are strictly unpredictable according to the laws of quantum mechanics, to control executive decisions. The brain would be a device for amplifying quantum unpredictability so as to achieve freedom of will. As soon as I begin talking about freedom of will, I'm entering a philosophical hornet's nest in which many famous thinkers and writers have been stung. But I consider philosophical discussion about quantum mechanics to be unprofitable. I'm asking a practical question to be answered by observation and experiment, not by philosophical speculation. I'm asking whether there exists in the brain a structure embodying information in the quantum states of memory molecules and hooking up these quantum states to an amplifier which translates them into classical neurological signals. If such a structure exists, then the brain is a quantum analog device, and the philosophers can continue to argue about whether it gives us free will. How should we study experimentally the working of a human brain? The best experimental tool is probably a human baby. What goes on inside the head of a 3-month-old baby? Anyone who has raised a baby knows the problem. How can we imagine what's going on inside that little head? How does it happen that that little head grows to almost adult size and capabilities in 2 years? In 2 years, it sorts out the bewildering variety of neural inputs from eyes and ears. It recognizes faces and voices. It masters grammar and syntax. It knows the difference between nouns and verbs. It learns how to exploit the weaknesses of grown-ups. In recent years, experts in child development have found reliable ways of communicating with younger and younger babies. A baby as young as 3 months old can communicate interest or lack of interest in something that it sees. If the baby is interested, it will move its eyes to follow the object. If it's not interested, it will disregard the object. Using this channel of communication, it is possible to prove that very young babies can already tell the difference between speech and noise, between known and unknown voices and faces, between familiar and unfamiliar syllables and shapes. As we move through the 21st century, it's likely that new tools will become available, scanning non-intrusively the brains of babies with high resolution in space and time. By the end of the century, we should be able to answer the question, how do babies begin to think? After that question is answered, we will have a better chance of answering the more difficult question, how do babies turn into grown-ups? Where does grown-up imagination come from? How does a brain become creative? Where do music and poetry and art and science come from? How did a monkey recently descended from the trees become aware of itself and of the mysteries of the universe around it? My dream is that sometime in the next 100 years, we shall answer these questions and understand how the brain works as a quantum analog device. Then we will be able to copy nature's architecture and build quantum analog machines ourselves. We will finally solve the problem of artificial intelligence as James Lighthill defined it. We will understand why digital artificial intelligence did not work. We will have the power in our hands to build machines that think like humans. But before that happens, we must think very hard how to use that power for good rather than for evil. Thank you.